Good afternoon, everyone. I will summarize about convolutional neural networks first, and then we will do some coding related to gradient descent, convolutional neural networks, and so on. Yeah. So before starting, we realized that when you think about a linear classifier, that means you have some matrix W, and you have the cat represented as a 4-number input. You can see 1, 2, 3, 4 numbers there. But of course, a cat image has many more numbers than that. But for the time being, let's assume that it can be represented using 4 numbers. And then we have the weight vectors represented as rows of this W matrix. You can see the cat's weights and the dog weights and the sheep weights. And there's a thing called bias also. So what we do is we take this vector and we turn it around and multiply 0.2 with 56, minus 0.5 with 231, 0.1 with the 24, 2 with 2, and then add this bias and get the cat score. And similarly, you get the dog score and the sheep score using the corresponding rows and the biases. So now the score is incorrect. That means it is saying that it's a dog because the dog score is high because we have not trained this. Training means adjusting them based on the errors that we make in classifying it correctly. If you properly adjust them, you should be able to see these weights when we reshape them into images as some kind of a cat image for the cat row, some kind of a bird image for the bird row, some kind of a car image for the car row, a blurry version after the training has happened. So we learned about the perceptron, and actually this is a linear classifier. And then we learned about bag of visual words and so on. And then two-layer networks, and we learned about these activation functions. Then we learned about multi-layer neural networks, and then briefly about the need for gradient descent. I will do an example today about gradient descent. And then we looked at the revolutionary thing that happened in 2012 with AlexNet. And then we looked at what convolutions mean. You see, you keep the kernel there and you multiply the underlying numbers with the numbers in the kernel, right? And then here, of course, because all these numbers are zeros, and you multiply them with 1 over 9. Here you have 1 over 9 here. So all the numbers in this kernel are 1 over 9s. When you multiply them with 1 over 9s and add them, you just get 0 because all the underlying values are 0. But not so here. You have 190. So when you divide that 90 by 9, and all of the numbers are 0, you get 10, and here you get 20, and so on, right? This we did. Yes. And then we looked at how fully connected networks like this, they have all the nodes in the previous layer contributing to computing one cell in the next layer. For example, to compute this, all the input layer nodes contribute, and so on. Then we looked at convolution operation where only a neighborhood contributes. And then we realized that when you mention convolution kernels, you just say 5 by 5 spatial extent. The depth extent is implicit because it is, if you have a 3-channel input tensor, we call them tensors, the depth or the number of channels of the convolutional kernel will be 3 input number of channels. Yeah, so then we looked at running multiple of those kernels, and then again another convolution kernel on this tensor. So you can see this convolution kernel spans the depth or the number of channels in this input, in this structure. Yeah, then we looked at how multiple kernels happen and the size of the output structure, and we obtained formulas for this. And then we considered batches, and we briefly studied about the AlexNet and how these convolution layers, 5 of them, are stacked in AlexNet, and then the nonlinearity, spatial pooling, and so on. So this structure of the AlexNet conpool 5 of them, and the 3 dense layers. Yeah. And then we looked at the padding thing. When we looked at got a formula also, P should be usually K minus 1 divided by 2, where K is the size of the convolutional kernel, for example, 5 by 5. And then we looked at the receptive field. It linearly grows with the number of layers. Yeah. And then we looked at the stride. That means you can go 2 pixels at a time, 3 pixels at a time, and so on. But usually it is 1 pixel at a time that we move, like so. Here it is 2. So that is also possible. That's called the stride. And we looked at that. And then we looked at 1 by 1 convolution. For example, this is a 5 by 5 convolution. And then you can just have 1 by 1 convolutions also. But remember that the depth is the number of channels here is applicable. Then we did this little example where we computed the number of learnable parameters. That's where we stopped. And then, of course, we did a lesson on epipolar geometry and so on. Now we are getting back to the convolution. So if we briefly summarize, so you have something like an input tensor that looks like a box, you can consider. So when you consider about this input tensor, we will have h times w, height, okay, width and the height, and then C in is the number of channels. For an image, it is 3, but later on in the network, it will increase. Yeah. So we have the kernel size kW and kh, but these are usually 3 by 3 or 5 by 5. And the padding, now this input structure is padded usually to keep the output size the same as the input size. That's the number of pixels for padding, and the stride by how many pixels this convolution kernel center move, and the weight matrix C out times C in times kh times kw, and this is given there are C out many filters of the convolution kernels, and then filters of size C in h times kw. As you remember, that's the filter must span, right, the input tensor, as we discussed previously. So it will be, if you take a 5 by 5 filter or something, that 5 by 5 will be like that, but it will span the whole number of channels here. Yeah. Yes. Then there is this bias also, bias vector, and the output size is C out times H prime times W prime. So we can compute this with the formulas that we derived. H minus K plus 2P divided by S plus 1. So it is important to remember these formulas and the typical values. People usually use a 3 by 3 convolutional kernels with padding 1 and stride 1. Or 5 by 5 convolutional kernels, that's also rare, with padding 2 and stride 1. Yeah, that's what people use. Okay. Then we will briefly look at max pooling. So max pooling is a very simple operation. Now assume that you have a tensor. This tensor size is, you can see 4 by 4, right? So if you do max pooling by 2 by 2 with stride 2, you initially pick a 2 by 2 window here, right? And pick the maximum value of that. Maximum value of that is 6. So you put it in the output here, 6. And then you move the window by 2 pixels. That's why you say it is stride 2. So if you move by 2 pixels, the window will land there. And then you consider the maximum value, that is 8. And then that 8, you put it here. So you can see this became 2 by 2. So size gets divided by 2 because of this stride equals to 2, right? Yeah. Similarly, the other two placements of the kernel. Yeah. Any questions about the max pooling? These are extremely important operations. Okay. So the max pooling summary also you can see h prime is h minus k divided by s plus 1. Yeah, that's all you need to know about that. Okay. Then we need to look at the gradient descent. So I will briefly talk about the gradient descent and do a very simple example of gradient descent. So maybe I should draw it afresh. I will draw it afresh. Any questions up to now? Are we okay? So now what we are considering is an important operation called gradient descent. Now consider a function like this, function like that. Okay. Now this function has two minima, as you can see. Two minima. So one minimum is maybe lower than the other minimum. So we want to find that. So consider this as the y-axis and consider this as the x-axis. Okay, this is x-axis. This is the y-axis. Okay. So what you want to do is to find the minimum starting from some x value called x naught. So let's consider this as my x naught. That's x naught. So the value of the function at x naught is, of course, this value, and that is, we call it fx naught, value of the function at x naught. Okay. Now, if you consider the slope of this function at that point, a slope of this function, to compute that, we have to draw a tangent to that, right? And this angle that it makes it the x-axis is the slope of that. So we can consider the tangent of this angle, right? That is the tan theta is the slope, if you remember. So it's a small angle. So therefore, tan theta at this location is positive. Gradient is positive. Gradient is positive. So in the gradient descent, we have to move in the negative direction of the gradient. So gradient descent equation is new x value. I will write xt plus 1 or something. X t plus 1 is equal to xt minus some constant, we call it the step size or the learning rate. So learning rate, LR, time gradient of that function. So I'm writing f prime to show the gradient at xt. This is the slope for the gradient, right? Gradient. Yes. So you can see we have to move in the negative direction of the gradient. Can you see that? We have to move in the negative direction of the gradient. Now at this point of x naught, we have actually two choices to move. Two choices. Right here, there are two choices. You can either move toward the right or you can move toward the left. Only two choices are there. So this is the positive direction, but remember you have to move in the negative direction of the gradient. So gradient is a positive value. So therefore we have to move in the negative direction of the gradient. So therefore the correct direction to move is I erase the whole line. Is that direction. You have to move in that direction. How much should you move in that direction? That is defined by this my eta or the step size. So assume that you moved that way and you obtained x1 at t equals 1, x1. Okay, now you apply that equation again. Again, you apply that equation. To apply that equation, we have to get the estimate of the gradient. So you draw a tangent to that. Still we realize that our gradient is positive. If the gradient is positive, we have to move in the negative direction of the gradient. Gradient times the step size. So I'm just selecting amount of motion, but you can have to actually compute. So here you get x2. Right. There again, we estimate the gradient. So you can see this is gradient descent, and hopefully right here we will stop moving. So sometimes you don't stop moving. So these kind of things are there. Okay. So this is what we are going to do now as the first implementation tonight. Okay. First of all, let's do it with manually using NumPy, and after that we are going to do it using PyTorch. Okay, so I have a beautiful function actually, and using that I will do it. I hope everyone is ready to do this important exercise. So this is manual gradient descent to find the minimum of a function. Okay, first of all, let me import NumPy as NP and import matplotlib as PLT. That's fine. Then define the function def f x, yeah, is, so I have a function. I have coded this before, so I coded it at home. So it's a good, very good, nice function to work with. Okay, x to the power of 4 minus x to the power of 3 minus 12 times x to the power of 2, 12 times x to the power of 2 times 15 times x plus 5. Okay, x to the power of 4 minus x to the power of 3 minus 12 times x to the power of 2 plus 15 times x minus 1. So let's, before doing anything, let's sketch this function. To sketch this function, of course, we have to put some coordinates, right? So I will say x equals np dot lin space, linear space numbers. So I want to have from space. I want to have numbers from -4 to 4, and I want to have about 100 of them, 100 numbers. That's fine. So now let me plot this. PLT dot plot fx against x. So let's plot this and see. Oh no. Oh, did I make a mistake? X to the power of 4 of 3, 12 x, oh, x squared, right? 12, okay, I put the stupid 2 stars there. That's a mistake. Okay, this is the function. So you can see it's a beautiful function. So you can start with some value and find the minimum of that function. So that's why this I took some time to be able to find this kind of a function. So can I give you a minute to do this by yourself? So please quickly do this. Get the plot. If you have any questions, please don't hesitate to ask. Can I have a yes or no answer whether you were able to do that? Have you been able to get the plot of fx? I hope you are doing this. Does anyone need any help or are we okay? No one is answering. Okay, I assume that you are able to get this. So now to the gradient descent, we want the gradient of this function. So def, let me call it gx. Okay, dfx. That's good name, right? dfx. So now let's try to get the derivatives. Now this is x to the power of 4. Derivative of that is 4 times x to the power of 3. I hope you remember the derivative of that. So derivative of uh, d d by dx, d by dx, x to the power of n, is equal to n x to the power of n minus 1, right? This is from early A levels. We have this. Is the derivative, right? So using this formula, we can find the derivative of that. Return 4x to the power of 3 minus 3x to the power of 2, because of this term. 12 times 2 is minus 24x and 15 for this one, and then there is a constant. Okay, that's the derivative. So what is the gradient descent formula that we had to do? So we had to start somewhere, right? We had to write x naught. X naught. So I will start x naught with maybe I like 0.2 or something, right? 0.2. I'm going to start x naught is 0.2. And then I need to have the learning rate, eta. It is like 0.1. That's the learning rate. Learning rate, this is the starting point. Initial guess. Now we had to write a for loop for I in range. Let's call it epochs. So the epochs I in range epoch. So let's write this number of epochs as maybe 10. Okay, just 10 is more than sufficient. Epochs e, yeah, correct. And then we have to write the equation here. But before that, let's print this. Let's print let's print x. Let's print x. Let's print function value, and let's print dfx also. We can print that, and the actual, yeah, that's enough. And we can do the gradient descent equation. This is the most important equation. X equals previous x minus eta dfx. Update rule. This is the update rule. And then finally we can okay, I want to do a plot also. Plot plot. I want to put a red dot there. PLT dot plot. I want to put a red dot there at x and fx at that. I want to put a red dot. This is a good red dot. Yeah. Then this. Yeah. Okay. So maybe you can pausing. PLT dot pause. I hope that works. Yeah, let's run this and see. Starting from the initial one. In the plotting process, we have updated and plotted, right? The initial one we have not plotted. So I want to plot the initial one anyways. PLT dot plot plot, and because it's the initial one, red. I will print that in green, blue or something. Okay. Yeah. So we can see this is what it has happened. It has not moved further. Okay. It has stopped, right? It has stopped. I don't know. After posting, you will do something. Oh no, my goodness. Oh my goodness. It is plotting again and again. Okay, I think I do not know how to do this, so I'm going to erase this. That visualization thing. Okay, not that. I want to erase this. Yeah. Then run again. Yeah, okay, we can see now how it has moved, and it has moved there. So it has not reached the minimum. So that means we don't have sufficient number of epochs. Or we can increase the learning rate a little bit to 0.2 or something, and it will go and yeah, go and reach this. So multiple times it has hit that. You can see it has been the function value has been minus this 153 for several couple of iterations, right? Almost there. So there at these locations, the gradient is almost zero, but you can see it is slightly oscillating here. Slight oscillation is there. You can see gradient being negative, positive, negative. So it is switching. It is iterating and switching, going here, here, like that, it's going. Yeah. Okay. So I hope the gradient descending is clear for you. So I invite you all to do this and understand how that is done. What is the meaning of that? Take a minute to do that, please. Is there any question? Let's clarify. Okay, now we are going to do an important thing from here. Before that, I'll put these things so that they are all in order, and then I will write the equation also. Gradient descent equation. X. I'll just write t plus 1, okay? As I wrote in the slide, equals xt minus eta f xt, right? That's the equation we are implementing. Okay. Now I want to write that using PyTorch first. Without AutoCAD. So I will explain you what this AutoCAD means afterwards, after I write this. Okay. So in order to do that, first we write this same thing. Of course, we have to import torch. We write the variant also. So no numpy anymore. Import torch. Yeah. Torch is the main deep learning library that we are doing. You can you can X as torch namespace torch dot namespace, the same thing. Then we can correct.
So I have a small question.
Yes.
Might be stupid, but I'll ask it. Normally, when we are dealing with this machine learning, aren't we dealing with matrices, mathematics? So here it just seems to be like a single point line, but
Yes, that's a very important and the most crucial question that you ask. We are dealing with matrices. Actually, we are not dealing with matrices. We are dealing with tensors. Yes. But I want to show you with this very basic thing what actually happens inside. So with a single variable, that's very important that you notice that. So as Mr. Madhapata mentioned, you can see that this x value takes just one single value, right? It's a scalar. So I'm showing you a function of just one single variable. But when you do this also today in the evening, you will see there will be so many dimensions in that. So and then we will be dealing with matrices and tensors. Yeah, thank you very much. We will soon see that. Okay. So right now you can see I'm using just using a torch and now I have plotted that. Now you can see when you get this number x, I'm going to say torch tensor, torch, not tensor. So you can see this is generally valid for other ones also. Torch tensor 0.2, we initialize that. And required gradient, no, so we will not initial guess, this is initial guess. And then the learning rate eta is fine, epox is 10, and then it's the same for loop that we run for I in range epochs. So you plot that, then the same equation, then I first of all plot the initial one also. We can do using plot this in x dot item. So because here these are tensors, we need that dot item. You can see that's a change. Okay, let's run this and see. We can see exactly the same thing that we got. But here also you can see I have coded the derivative of this function. But as mentioned, now these are going to be very complicated functions. We can no way write the derivative manually. Manually, you can never write. So we have to get the power of PyTorch to be able to automatically compute the derivative. So that is called autograd. So if you ask me what is PyTorch, it is a automatic gradient computing and backpropagation machine. That is what it is. So, all right, now let's do that finally. So here I'm going to do gradient descent. Using autograd in PyTorch. Okay, now you will see I'm going to do a very crucial change to the code. So I can copy the whole code, that's not a problem. I can copy the whole code and I will not have this. df is no longer there. df is no longer there. And for this one, I will write, okay, I will write the so-called forward pass. The forward pass I will write. So that forward pass is, we call it the forward pass. Forward pass y equals fx. Okay, y equals fx. We compute that value y equals fx. To compute the gradient, we have to do one single function. That is, you will say y backward. That's all. That's all. So it compute the gradient. So now now we have to, without using PyTorch's gradient computation, then we will do the updating and zero the gradients also. Clear the gradients for the next iteration. That one, yeah, but that can be within this or outside this, that's not a problem. All right, so now you can see magically I do not have this. So this gradient computation update, I am saying, I don't say as I said here, this is my manual gradient computing function df. So in the update equation, I'm using dfx. At that point, what is the gradient? But here I don't have to do that. I'm just saying x grad, and it will know how to compute the gradient. Okay, so x grad means gradient of this f function with respect to x. So what mistake I made. What is the problem?
But you have to define y as a tensor.
Let me see. Okay, I do not know. So I will ask Flo to compute that, find that. What is it saying? I don't know. When it changed, I don't think it didn't change. Yeah, I don't know what mistake I did actually.
I think there was a parameter it mentioned that you have to add it. If you go back to that line where that error was, maybe it added a
Right
parameter.
now, right now,
Uh,
right here.
that's what it said, but it doesn't seem to have added.
I don't know. Anyways, so now it's working. So I do not write in this fashion here. I will write x minus theta. I think having this inside the no grad one is the problem. I think the zero gradient. Oh, is that a problem?
So there is an underscore after the zero. Maybe that's why
That
red
is
dot.
that's
That's correct, is it? Red dot zero underscore and then
uh, here's the thing. Yeah, so now it's okay, right? So this I actually I don't understand that. Okay, why that is happening. So maybe this is okay. Yeah. So all right. So now what I want to explain is not that. What I want to explain is this line that when you say y backward, we are able to it is computing the gradients by itself. X dot grad is available to us now. So you remember this has been defined as a tensor, and we have said required grad to true. So therefore, when it is doing this computation, it computes the gradients also. So you can see uh, x dot grad prints the gradients. You can see the gradients have been printed. Yeah, like equally to this. So it has automatically printed those gradients, and these are correct.
so
Is that point clear?
I think
Yes.
in that y you can see they have defined it as I think a tensor. If you go to that y definition, I think I saw initial y definition it was defined as
I did not define why.
no, it sort of I saw it somewhere, some kind of definition. Unless I made a mistake. I saw some definition here. X torch dot tensor and then
Yeah,
data and
yeah,
requires gradient is equal to
yeah.
true.
Requires gradient true. Yeah, that's true. Yes. This is very, very important. So if you say requires gradient false, it will not compute the gradient. So if you say false here, it will not compute the gradient. So see, now it will say grad is not available. That does not have the that required. Yeah. So therefore, you have to say required grad. Okay. So I hope that's okay. Forward pass and the backward pass and so now you can see if you are doing a gradient descent using PyTorch, you do not have to compute the gradients by yourself. Just saying backward is sufficient for it to compute the gradients. Okay, now let's get back to the slides and see this one. So now we are going to code this one, this linear classifier. But one thing is, because we have to use this data set called CFA, so it will download by itself. So you should have some bandwidth left for that. And also, you need a little bit of coding to get the data set ready. So that's what I'm going to do now. It's a linear classifier using CFA. That's what I'm going to do now. So with manually. Let's get to doing that. So a little bit of coding. So part 10. So first of all, we have to import these things. Import torch. By the way, I asked you last time to install torch. So if you do not have the torch installed, I will show that also. A little bit of the thing that you have to do. So you go to the torch website, iTorch website, and there is a mm, install, how to install. Getting started or something, I think. To do that, you have to click what you have. Stable one, please select that. If it is Windows, select Windows. Maybe you are most probably you are using a pip and Python, and then CUDA version if you have. Otherwise, click CPU. If you have CUDA installed, one otherwise CPU. Then it will give you the code. So pip3 install Torch Vision like that. Torch and Torch Vision. So like that, you have to run this command. Then only you can get PyTorch working. So import torch. Then we will import the torch vision, and then we'll import torch vision, the transformers are transformers. I'm not too sure. Transforms, not transformers, transform. So we are going to transform the data set. That's what we are going to do. Transform. So transform.compose, transform to tensor. To tensor, and to tensor, then transforms to normalize. Not normalize. Normalize. So normalize 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. So when you have a data set, you normalize that. So 0.5, comma 0.5. This was for the channel 0.5, and so on. Means and the standard deviations using which you normalize. Okay. This is okay. Let's run this and see. This is the transform.
So 0.5 means the maximum value will be 0.5 or
No,
0 to 5?
we are normalizing the mean to be 0.5 and the standard deviation to be 0.5. So for
Okay.
different data sets, there are things that people know. Okay, you have to normalize it like that to get it working, for things like that. So this is don't think about it too much. From the internet, you can see how to normalize each data set. So there's a thing called batch size. How many images you feed at the same time? So we talked about this in the slides. Batch size equal, let's call we take the batch size of 50. Then we have a train set. Okay, so it is getting the train set from yeah. So now you can see when it's downloading, and I think it is applying this transform also. That's a train set, and then we have a train loader. Torch it is data set train set. Batch size is batch size, and shuffle is true, and number of workers 2 or something. Number of workers 2. Okay. So all right. Then the test set. Okay, it's giving me the code. CFR train root data train download true. Transform is transform, and number of workers is true. And then we have the classes. Okay, these are the classes of the CFR 10. So this is the thing. It will download. If I have it downloaded on my machine, it will not download. Oh, Service unavailable. Okay, let me see what is the problem. Oh, that too.
So do you have to define your download folder? Like, do you have to create the folder automatically, or it's creating slash data
No, it will
root?
work. It will work. It will already create those data folders. That is not a problem. Maybe it didn't. Correct. These codes I wrote some time ago, so I don't know something. Did I miss some parentheses or something? It puts a dry catch. Still, it's not.
Is the name correct, sir? CIFAR
Yeah,
hyphen 10?
that's correct. That's correct. Let's do an internet search and ask. This is a problem is what it's talking about, right? This is, sorry about that. I should have practiced it. Oh, it's trouble, right? Shall we do? Trouble. Let me once again try it, ChatGPT. Otherwise, I think we have to. Not we won't be able to do this tonight. It's unavailable. So put that in ChatGPT once, and if it doesn't work, you're going to stop it. Stop. It's fine. I'll do it next time.
So there's a
Asking to,
method where you can manually download the
but yeah,
dataset
yeah,
and then
it's asking to manually download that.
I think that's a security issue from the website. It's blocking it.
Yeah. Let's manually download it, and try once again to manually download it. If it doesn't work, oh, not too much trouble, I think. And it's about 1 GB also. I don't want to make a mistake there. So this code, I'm sorry, I cannot write now. So we will move on. Let me try whether we can work with MNIST or something. That one is downloading, right? Yeah, we'll use MNIST. It's not a color data set, that's okay. Okay, let's use MNIST. Classes are these things. Train set, test set, train loader, test loader. Okay, now it has been downloaded. It's a small data set. So why don't you download it now? Yeah, so it's not a coding problem. It's a URL problem. So when you download, it will keep it in data like this. So this code I'll send over the chat so that it's easy for you. Okay, now we are ready to move forward and do some computations. Okay, so maybe we can do some plotting also. Import matplotlib as PLT and numpy. I want to plot some definition imshow. Okay, so it is already knows what I'm going to do. So this is the imshow function. So you can get some images and show them. Data iterator, train loader, get the train loader, and we load some images and labels, and you can show labels. Oh, whether there's a version problem also, you know. These are the previous codes that I did. Try to correct this. There's a problem here. Okay. That's the thing.
In the top code that you were doing that standard deviation thing, it's a single. It should be single, I think. Yeah, instead of three. Yeah, single. It's a single. I don't know
Single
what
number.
about.
Yeah,
Yeah.
it's now color from color images we have changed to.
Yes, sir.
Thank you very much. This also anyways, so all these data related problems are cumbersome. So these are the numbers. So it displays some of them. You can see these are handwritten digits. The next, what we want to do now is to write this linear classifier on that. So let's do that. Import torch. So you can do it in NumPy also, but we will do it with torch. Import torch dot neural networks as NN, and import torch dot optim as optim, so optimizers. Import torch vision. Maybe we will not need it. We have already imported transforms, then matplotlib. Okay, importing is done. Then define the network parameters. Define the network parameters. So number of input dimensions, C in or D in, we can consider as 28 by 28 for the FIFA MNIST images. Then K is number of classes. Then to initialize the weights, we can define a standard deviation, maybe 1 10 to the power minus 5. or something like that. So we can see whether that works. So first of all, our W matrix, W equals torch Dean times K. So remember, that's the size of the matrix that we should have. See, this is the number of classes is 3. Input dimension is 4, right? So that we have to define in that fashion. So this is my W, and then I need the B equal to the number of classes, right? So here you can see 1, 2, 3, depending on the number of classes. Yeah, that's how the weights and biases are defined. Then we can consider iterations. So we can call it epochs. Epochs. It's 5, 10 or something. And then learning rate. It's okay. It's saying 0.1. Maybe it's too much. I want to keep the loss history also. Loss history. Loss history. Okay. Then now the training loop. Training loop. So for E in, okay, epoch in range epochs. Okay, we keep the, okay, these are, oh my goodness, put everything, it coded everything. I don't want that to do. I want to go step by step. Running loss, the loss of this, we will see what the loss is. Now, what we need to do is, for so I data in enumerate train load. So we are getting data from the so-called train load that we defined. So you can see from that we can get the inputs. So you can see everything it's plotting, right? Inputs, because everyone is writing this kind of code. Labels, inputs, labels is data. That's my data. Then we have to get the number of training data. We anyway get that NTR. That's a batch size, of course. Input.shape, the batch size. And then we have to change the shape of the training. So xtrain equals inputs v NTR minus 1. So whatever the dimensions you keep, but show it as well. So 50 vectors, 50 vectors. Yeah. Then Y train, we have to get the one hot labels. One hot means Y train torch zeros NTRK. So like that. So you can see for every training examples, we keep 10 numbers. Only one of them will be 1. So you can see that is the operation it is doing. Okay, then the forward pass. Forward pass, it knows what I'm doing. So scores. So you can see xtrain matrix multiply with W times B. This is a score. I will call it Y pred. Y pred equals xtrain matrix multiply B. So actually, I will write MM here, not MM, because we are using torch. MMW, matrix multiply W, that's correct. Plus B, then the loss calculation, mean squared error. We want to do mean squared error. So loss, get the difference between train and predict and get the power and the mean. So you can see that. And then you add the loss history to this loss, you add that. So you can write running loss. You can keep the running loss also. Running loss plus C equals loss dot item. Running loss we have to keep. Okay, sounds okay. Running loss is that one. So, right. Okay. Running. Correct, right? Running loss. So now we have a forward bar pass is correct. So I'm going to manually implement the backward pass. So you can see it's a square loss. So I will not go into too much details, but mm, this one is the gradient because it is a square. So you just multiply by 2. Gradient with respect to W, that W. So these equations I can maybe show you later. Grad B is also correct. And then finally update the weights and biases. Minus equals means W equals W minus and bias. Okay, like that. So it's done. So let's do some print. Okay, that's correct. We can do some printing now. Print, yeah. So it does the printing. It knows that it has to print. Then we can finally plot the loss history. X label iteration loss. That's enough. Now you can evaluate the model on the training set, test set. Yeah, so total loss. So okay, let's not do that part. First of all, let's train it and see. You should be able to see a graph of the loss graph. It will be a very noisy graph, but it should generally go down. Loss should generally reduce. I should have printed right here. So first epoch loss, it's printed. So you can see loss is slightly reducing because just a linear network. Okay, so the loss will not be drastically reduced. By the way, now if you want to compute this manual implementation, do I have that in the slide? Let me show you that the equation that I used to compute the gradient. Has done how many iterations now? 4. loss is reducing. Let's write it. What I want to explain, okay, now it has run, so you can see the loss has reduced. What I want to explain is these equations that I have written here. Now our loss is y pred minus y train squared mean, right? So if we write that, so my loss is sum over the batch. Okay, sum over the batch. I will call it, then get the mean. So that variable I called NTR. No? NTR. Y predicted means Y pred. Just that Y pred. And then Y true square. Okay. Y true is a constant, predicted value is what we want. So now you can see because of this square, partial derivative of L with respect to Y, P, P. Now in this case, we consider all other variables as constants, right? When you are getting the partial derivative. So only this variable matters, right? All others are constants. So therefore, because of this square, you get 2 here. 2 divided by NTR. Summation YP minus YT. You can see that, right? So, okay. So then we had the other equation. So you can see this is the correct one, right? Mean means 1 divided by 1 over NTR mean. Then I'm sorry, this one. So this is the gradient. Then you can see gradient with respect to W. How do you get the gradient with respect to W? Um, so our equation was y predicted is W times the input data plus B, right? And now you can see gradient with respect to W of yp, that is partial derivative of yp with respect to W is just x. But now if I ask you, given this, what is the partial derivative of L with respect to W? That is what we want in the gradient descent, right? That is partial derivative of L with the chain rule with respect to P times partial derivative of yp with respect to W. Can you see that this is just equal to x? This we have already found. So these two things we have to multiply. So that's what we have done here. Not we have done, it just prompted. So we can see you get the x and multiply by what you got here, here with the matrix multiplication. And to get with respect to b, it's just one, okay, because it's wx plus b. So you don't have to, you just have to do that. So you can see these are the backpropagation, so-called backpropagation that we do. Yeah, and then of course update for the weights and this. So you can see it's reduced. So now after that we can, if you like, we can predict, calculate the accuracy on the training set and calculate the accuracy on the test set. We can do that. So I think it will give me the code, calculate accuracy on the training set. So we can do that by it is using let's I don't want to spend too much time for that. Calculate the test set. I will explain that afterwards. Okay. So here you can see correct ones it sets as 0, total it as 0. Get data from the train loader. You get the images and the labels, so shape and so on. That's okay. And then you can see uh, predicted torch max y pred. So how do you predict? Y train times matrix multiply W plus B. So this is the equation that we had in our slides at the very beginning. No? When we did the linear classifier. Wx plus b, right? Wx plus b. That's how you get that. So I hope you remember Wx plus b. That is how you predict. So x times, of course, you have to use matrix multiplication, and then when you predict, you get the maximum value. So in under what class we get the maximum value. So that's what is so here, right? So we got the maximum out of that, right? That's exactly what we are doing. And then other things that you do, and then for the test set also you do the same thing by calling the test load. So let's see the accuracies. So it must be greater than 10. If it is greater than 10, it has done something. If it is less than 10, of course, we are in trouble because there are 10 classes. Wonder why it's taking such a long time. Computer is having trouble now. Anyway, in the meantime, I will post this code also in the chat. If you made a mistake, you can use that to correct. Yeah, okay. So training set is very high, test set is also very high, right? It's generally very good. Okay, so this part also I will copy with the chat. Okay, so I hope you understand that we did a very simple linear classifier, and of course we used PyTorch, and here but we did the manual gradient computation, but we didn't have to do that. We could have just without using this manual backpropagation, we could have just computed the gradients using PyTorch. So that we don't have to do right now. I will show, upload this code also after the class. Let's go back to the slides. I had to spend quite a bit of time there because there was a small error. Okay. All right, now let's look at some existing architectures, and then I plan to somehow code them also. Hopefully I'll be able to do that today. Existing architectures. So now let's take this very first architecture called Linet 5. This is a similar architecture due to Professor Jan LeCun. This is one of the very first convolutional neural architectures that he did for recognizing handwritten characters. So this MNIST dataset was the one that we used for that. Okay, so let's do this. Try to understand this. Okay, so you can see the input is 32 by 32 image, and you can see after this convolution operation, the feature map size is 6 times 20 times 20. Okay, so let me ask you briefly, what do you think is the size of the convolution kernel? No padding. Size of the convolution kernel. What do you think is the size? That means K. So if someone can type an answer, I'll appreciate that. Well, that's okay. I will give you the answer. So since the 32 by 32 has reduced to 28 by 28, we know that it's a 5 by 5 convolution. So remember now when you have an image and you want to keep the kernel here, right? You can only keep the center somewhere here if you don't have padding. If it's 3 by 3 kernel, you can keep the kernel here. That's all. So you cannot keep it earlier at an earlier location than that. So you can see you lose one row of pixels here, one column of pixels, one row of pixels, one column of pixels, one row of pixels, right? So if it is a 3 by 3 kernel, if you don't do no padding, your resulting size will be 2 less from the original image size, because a row from top, a row from bottom, a column from left, a column from right will be lost. Similarly, if you use 5 by 5 kernel, you can see you will use 2 rows from top, 2 rows from bottom, 2 rows from left, 2 rows from right. That's why you get a 28 by 28 image. So therefore now you can see it is a 5 by 5 convolution that has been done. Convolution has been 5 by 5. So those days they called it subsampling, but you can see the size of the feature map or the tensor has reduced to 14 by 14. So therefore you can see the subsampling that they must have done is 2 by 2. 2 by 2 max pooling with type 2, right? 2 by 2 max pooling. We can say max pooling, okay? They call it subsampling. Max pooling. Also, one more thing that you should notice is that they have run 6 convolution kernels. 6 convolution. That's why you have 6 of them. 1, 2, 3, 4, 5, 6. So due to max pooling, it does not matter. So this 6 remains the same. 6 remains. And then again the convolution. So what is the feature map size? 14 by 14 to 10 by 10. So because there is a reduction of 4 from the width and height, we know that again it's a 5 by 5 convolution that has been done. 5 by 5 convolution. Again subsampling. So subsampling by subsampling, you reduce the feature map size. So feature map size has become 5 by 5. And then you can see it is a 2 by 2 max pooling that has happened by 2 max.
So, can we in this analogous to sort of signal processing, like we have some input data, and then we are doing some kind of different signal processing at each stage?
Exactly. So in signal processing also we run filters. Those filters are convolutions actually. So here also we are running filters, but these filters are convolutions, but they are two-dimensional convolutions. It is exactly the same, but we can see we are running convolutions and we are downsampling the signal also. In regular signal processing, you don't do the downsampling like that. Especially if you are doing acoustic signal processing or speech signal processing, you don't do downsampling. You keep the sampling there. Here we do that. So there is a difference.
Okay, so thank you.
Okay. All right. So now, so you here now we have 16 times 5 by 5. So altogether you can see its size is 5 by 5 is 25, 6 is 400. 400 nodes will be there. 400. And that 400 is connected to 120. That 120 is connected to 84. That 84 is connected to 10. So let's try to compute the number of weights. How many weights are you being used here? Let's compute that. Learnable parameters, okay? The number of learnable parameters that we are using here. Okay, so for the first 5 convolutional layers, how many learnable parameters are we using? The convolution kernel sizes, because remember this is the black and white image. So the number of channels in the black and white image for the grayscale image is 1. So you have scene is 1, and these are 5 by 5 convolutions. Output number of channels is 6. That many convolution kernels are there, and we have to add the bias. 6 as the bias. Okay, so let me go back, take you back to the slide we had about this convolution summary. So you can see weight matrix is kh times kw is a convolution kernel size. Cin is the number of channels, and that many convolution kernels are there, right? C out times Cin times kh times kw. Okay. So because of the biases you have, I have that, and you can see. Let me do a brief calculation and see how much this is equal to. Uh, it is I don't want to mistake it. 25 times 6 plus 6 equals 156. I'm ashamed of myself. I used a calculator for that. 156. 156. Due to this convolution operation, due to this convolution operation here, okay. Due to subsampling, do we have any parameters in the subsampling? Due to subsampling, number of parameters is 0. Then again, there's a convolution operation that is happening here. You can see in that convolution there are 16 output number of channels is 16, and so the depth of the input now depth is here. You can see 6 is the depth, right? 6 depth is 6. So you can see we have to write 6 times 5 by 5 convolutions. We discovered that 5 by 5. And how many convolution kernels are there? 16 of them. And we have to add 16 as the biases. Okay. So now we will have 6 times 5 times 5 times 16, 6 times plus 16. You have 2416 number of parameters, 2416. Okay. So that is the parameter count for this convolution operation. Okay. Then for the subsampling, we know that there is no parameter in the subsampling, and the convolutions are over. And then fully connected. Now this output feature map size is 400 to 120 fully connection. That means 400 is a massive number of weights. 400 times 100, all are connected, right? 120. Output node count is 120, so therefore you will have 120 biases. So how much is that? How many meters there? Let me do that computation. 400 times 120 plus 120. So that is 40,120. 48,120. Good. Now you can see there's another connection 120 to 84. Now it's easy for you to calculate, right? 120 times 84 plus 84. That's equal to 10,164. Then finally, you have this one, 84 times 10 plus 10. That I can calculate with the calculator, 850. So altogether, compute the total number of learnable parameters. We have to add this 156, this 2416, this 48,120, this 10,164, and 850. Then total number of learnable parameters is, let me add that then, 56 plus 2,416 plus 48,120 plus 10,164 plus 850. 61,706. I hope that my calculation is correct. That many learnable parameters in this. It's a very small number in the current standards. Okay, so this is MNIST, and you can see it has two convolution layers and two max poolings, and then fully connected layers. Yeah, so we can compute, we can write that. So we will start. I will start writing that, and then we can take a break after that. So MNIST. Linet 5 like MNIST, that's what we are going to code now. Five like network, CNN for MNIST. Okay. So a little bit of annoying things are there, loading and so on. This importing of things I will copy from the previous one, and the data loading part also I will copy. Copy this. Okay. And now let's define the Linet 5 class. So okay. So we are using Python classes now. Class. Okay. Class. Linet 5. Linet 5. And it is from nn.module. So please learn about these things a little. Python. So it is coding everything for me, but I do not want that. Def. So this is called the init. So let's just briefly do this. So assuming that these are things that we need to do in Python. So in that, so we have to say super init. That's okay. And then first of all, the first con layer self. This is what you need to see. Con1, first convolution layer. Con1 is a remember it is a 2D convolution. Input number of channels is 1, output number of channels is 6, kernel size is 5. So if you understand that, I think we are through. So for that we have to write nn con2d con2d con2d. So in channels is 1, out channels is 6, and the kernel size is 5. So this is an important thing to note. Okay. So let's briefly run this unmatched. So you can see here in the slides, that is what we exactly saw that. So here you can see the output number of channels is 6, input number of channels is 1. How many convolution? What is the size of the convolution kernel? 5, right? So that's exactly what we wrote. That's convolution layer 1 that we want. We had to define the first pool layer. Then after that first pool layer, self dot pool 1. So it's 2 by 2 max pooling. So actually, Professor Yanlikun used average pooling. So let's use average pooling here. NN AVG pool 2D, 2-dimensional average pooling. And then the kernel size is 2, stride is 2. Kernel size, you know what this first, okay. Okay, kernel size is 2, stride is 2. Then comes the second convolution layer. In the second convolution layer, you can see the input number of channels is 6, output number of channels is 16. The size of the convolution kernel K is 5 again. Con2, now I will just hit. Yeah, this is correct. Hit. Then you have the pool 2. Pool 2, the same thing, so size 2 every 2. Then we have the fully connected ones. In the fully connected one, we have to connect from input number of features is 120 is correct. Input number of features is 400, right? 16 times 5 by 5. 16 times it is taking 4 by 4. 16 times 5 by 4. times 5 and output reaches 120. That's the first fully connected layer. Then the second fully connected layer, 120 to 84. Third one is okay. Now we have just defined these layers. We have not connected them. So we have to write the forward pass. In the forward pass, we will connect and finally compute the output using these layers. So I will request you to please code this by yourself. This is very important, this part. Any questions up to now? You are most welcome to ask questions as you always do. Okay, so let me write the forward function. Forward, so it takes x as the input. Okay, now we have the input x and we feed it to the first convolution layer. And of course, remember we have to add the nonlinearity, that is the hyperbolic tangent function. So I did not describe that there. So torch and okay, we can add ReLU also, but we'll add Professor Anand, but he must have added hyperbolic tangent and hyperbolic tangent. We can change to ReLU later on. This is what we need to do. So put x into the con1 layer and apply this hyperbolic tangent, and you get x out. We think you get x itself out. Then we have to apply it to the pooling layer, right? Pooling one layer. Then the second convolution layer, you take this x and feed it to the second convolution. Of course, you have to add the nonlinearity, hyperbolic tangent, torch, and h. Yeah. Okay, now the convolutions are over. Now we apply the second pooling layer also. Now we have to view this as a 400 tensor. This is very important. I know they will treat as a 16 times 5 times 5, comma minus 1. I hope it will work. Then we can apply the first fully connected layer and then apply the hyperbolic tangent function, second fully connected hyperbolic tangent, and then we can just get the output as a third fully connected layer and return next. That's all. Okay, now we have completed the convolution neural network with 2 convolution layers followed by pooling layers and 3 fully connected layers.
So I have a question.
Yes.
Normally, when you are doing this deep learning coding or machine learning, we don't normally define all these things. We use, I think, predefined models. Is it that, or is there?
Yes. Yeah, that's a very good question. So now, in this space, I'm teaching you how to do a model by yourself and train it from scratch. Yeah, we fully training that. Then, as you are saying, then later on, maybe not this week, next week, I will show you how to do this using pre existing models, load them and use it for your work. That also I will show.
Which approach is more like efficient? Is it this one or the other one?
No.
Accurate?
The other one is efficient. Other one is efficient. This is like I'm showing you how to use manual calculation. Then you can use a calculator later, right? This understanding is I thought is important how to manually code a network and train it from scratch.
Okay, sir.
And so because this is a very small network, very small data set, we can manually code it and train it from scratch. Yeah. Then the data setup is required now. Okay. So this is uh, it's working. So data setup we'll copy from the previous one because we had a lot of problem in the data work. These transforms and class names and all these things we'll copy. There's a little thing that we had to do because assuming 32 by 32, we had to do some padding. So the transform that I want to do is not this one. Transform that I want to do is transform.pad. Transform.pad padding equals to, because the MNIST data set is 28 by 28, but we want to convert it 32 by 32 because to match with the slides. Because here Professor Yamlikun has said 32 by 32. Actually, it is 20 by 28. So to get exactly the same thing, I'm padding. Okay, so padding is done. Then batch size is okay. And so train set, test set. Yeah, okay. Train loader, test loader, those are okay. Okay. So now we have to start training. So we do a little bit of setup first. So device, I have the CUDA. So otherwise you have to use CPU. So you can see the torch device. CUDA, if torch CUDA is available, otherwise use CPU. So then net model. Okay, let it be called net lineage 5 to device. So you cast it to that device. And then criterion cross entropy loss. What is the loss that you're using? Mean square is what we used in the previous example. Now we will use the so-called cross entropy loss. Then optimizer is required. Optimizer, we'll use optimizer. The good optimizer that we use is the Adam optimizer. It's very easy to use. So because of that, we will use the Adam optimizer. Adam optimizer, model parameters. Learning rate is 0.01. Yeah. It will go -8. So now we have to define the losses. Logging. For logging, we need these things, batch losses, because we are feeding by batch by batch. Nothing. Train loss, train losses. Train losses. Train accuracy, maybe. Train accuracy. And then test accuracies. Yeah, this one. And then the training loop. Training loop. Epochs. Let's maybe 10 epochs. For epochs in epochs. That's what we do, as you remember from last time. And then we have to say, oh, okay, net dot train. So running loss we keep 0, and correct ones we keep 0, and so on. And total we keep 0. Running loss, we can keep it as 0. And then so we have to get data from the train loader. For data, last time also we did that. Data labels in train loader. Computed everything. The problem. in train loader, we want to write step by step. So data, comma, label, data to device. So we have to do the put the data in the device. It's GPU or CPU to device, and zero the grad of the optimizer zero grad. That's okay. Then output to compute by saying model data. So now this is the output. Then loss. Now we have the criterion, outputs and label. That's how we call it. So loss, and then loss backward. Then optimizer dot step. That's all you have to do. So you can manually do these things also by using looking at the previous examples that we did by manually computing the gradients. But why should we now that we have? So batch losses, append loss dot item, running loss, append loss item but they plus dot item. Mm, so training losses append, okay, and divide by the train loader size, and then you can print that. Then we can do the validation, net eval, and the correct runs, zero total zero. And so now you can see we do the same thing. So I will hit oh, that's all. Test accuracy. Okay. You can plot also, yeah, giving all these things. I will send this code when we confirm that it's working. So you can see AI prompting is okay. Here is simple code. Yeah. Now, yeah, okay. That's all. So now let's run, and I want to run for maybe 5 and see. I hope it is correct. We did too much AI prompting. Module parameters. Empty parameter list. Let me see it optimize the problem. So
You had to define it as a list.
I think so.
Do you need to put the square brackets both sides or no need?
I think these parameters for the Adam have to be defined. Trying to see how to define this. So there are certain number of parameters that you need to put. So we will use the help of this set to. Adam Optimize has two parameters, beta 1 and beta 2. This reverse. What is it? Not the one that is correcting. Okay, let me correct the name and see. What happened to the Adam? Did remove all these things. Adam. I need to find that out. What happened with Adam? Let me see. Yeah, it's computing, so let me find that out because I didn't understand that. So we had to look at the so-called optimizers. You don't have to do that. Just give the model parameters and add them. Only the learning rate has to be given. So this is a variable 1, variable 2. What to be given pattern. So ask this. Okay. I'm sorry that I don't understand. So yeah, let it run. So it is optimizing. So you can see the accuracy on the training set is already 98%. That is 97%. So since it is working, I'll put this code also in your one.
So what is a good accuracy rate for this kind of model?
Yeah, so now that's a very good question. So in the training set, there are 50,000 examples, right? So one of them is 1, one of them is 2, one of them is 0, and so on, right? So this is 6, 5, 6, 5. So for instead of this, if we say 1, that's an error, right? For this, if we say 5, that's correct. So number of correct ones from the total, that's the accuracy. And there are two accuracies, one for the training set, one for the test set. Using the training set, we train the model. Using the test set, we test it. I hope it is clear.
Yes, sir. No, I'm just asking, like, given current industry standards, like generally, what is an acceptably good?
Yeah. Again, that's a very good question. What is an acceptable accuracy? You have to qualify that with the particular data set, right? With the particular data set.
With the data set. Okay. So if the data set is very like messy
complex,
or complex, then
that's right.
you can expect a very high accuracy.
Yeah. So maybe we have leaderboards. Say for 100 leaderboard. So leaderboard will, I don't know whether I have not tried this. So leaderboard. So gotten one, right? 100%. So now 100% has gotten 5 years ago. So that, can you see that? That's for CIFA 100. So like that, for different data sets, there are accuracies that people have, leaderboards are there. Mm. So from somewhere you have to find the accurate leaderboard. So data set card CIFA 10. So maybe we can look at other different data sets.
So if you are like doing some medical analysis, then we have some data, and now we are doing we find some accuracy. Let's say 70% is. Then do we assume it's good, or do we need to improve on that, or does it that depend on certain requirements?
Okay, it depends on the requirements. Now, if you're asking what is this data set like? Is it a segmentation based data set, like for example, cancer nodule detection, or yes, no data set?
The first one, sir.
So if there is a cancer nodule, we have to locate those cancer areas, right?
Yes.
Then you can see the overlapping is also important. That means how much is the overlap? Then what do you consider correct as when you overlap? So this is a slightly complicated data set that you're talking about. Here, if it is 1 for 1, it's correct, right? If it is 0 for 1, it's wrong. So I mean that's very obvious. So for some data set is not like that. This data set dependent. So if you think about maybe you have mm, light or something, and then there are these cells, let's say cells, and then our detection, and they have they have segmented. So our detection is like that. Let's say some overlap is there. So you can see. So you have to get the overlap depending on the total area, right? Here the total area. Overlap by total area. So we can consider something correct if this is 50%, right? 50% overlap. So like that. So if it is 50, you consider it correct. Then you can define the sort of so-called, we call it precision. Precision we can define. So it is data set dependent. So each data set will have leaderboards that show this.
Okay, sir.
So we cannot say whether without looking at the data set and looking at the leaderboard, what is a good number, unfortunately. We can now see, so loss has reduced, and you can see the training error is usually higher than the test error because test data set you have not seen. So you can see the training loss has reduced, and then you can see the training accuracy has reached 99%. Test accuracy is like that. Usually we do a validation accuracy. So the validation accuracy start decreasing, you stop training. So here you can see from here it is starting to decrease. So you have to stop the training from there. So that's why we use the so-called validation set. The test set we don't touch, but I didn't want to go for that complication now. Okay. I hope that this part was clear to you. I think already 8:17. Um, Maybe I will keep on going and stop because now there's no use taking a break. I'm sorry about that because of this coding thing. It took time. I couldn't give a break. So we defined this class, and then we had the forward class, and then you can see after calling that class, so sort of instantiating an object of that class called net. Then what we did was we said when you say net, it will run this self, and then it will initialize that net. And we have net.train because it is from the neural networks class. And then you can see we have the data from the train loader, we get data. So to get the output, you just have to say net data. Net data. It will automatically know how to get the output from here. And say net data. So these are things that we have to remember. Just by looking at the code, we cannot know those. Net data.
So I
And
have a
then,
clarification.
yeah.
Now, every cycle or epoch, the efficiency or accuracy, it seems to be increasing. So the training set and the test set, does that mean this test set and the training set are changing dynamically on each
Oh, no,
cycle?
no. Okay, train set and test set are not mixing for sure, because we have loaded it differently, right? I mean, see, like train set and test set, we have loaded different sets, because these data sets, they have defined what is the training set and what is the test set. We have loaded that, and you can see in this we are only using the train loader. But then when you are getting this from the train loader, when you are getting the data, it will do some shuffling. And it will load me a certain batch. Load certain batch. So because we have set the batch size, right? When you create the train loader, we have created the batch size as 50. So it will load 50 for me, and that will be loaded randomly. Yeah, that's a very, very important question to note. So you have 50 of them here. And then with this 50, we are getting computing the output, computing the loss, computing the backward pass, and optimizing, like what I did in the gradient descent. And then we can compute the losses. Loss.item, we can put it in, not compute, put it in.
So how did the 50 come, that number?
Number,
Did you
yeah,
define it?
we defined it, yeah.
Okay. Okay, you
Size is
defined.
50.
Okay, sir.
That means at a time we take only 50 images. So that's why we looked at that in our examples. Remember, we considered this batch of 4 images. Remember that? Batch of 4 images we considered, right? Then depending on that, each image is the color image seen, and we considered batch of 4 images. That 4 is what I defined as 50 there. 50 there. You can change that. Then different kinds of things happen. So when you change that, I'm using CUDA because I have a GPU in my computer, a small GPU. So that's why it's fast, or maybe in your machine it will be slower. This is a full piece of code that does almost all the things for a convolution neural network, and we have fully trained that from scratch. Trained from scratch.
So after you train the model, then we need to save the model and then we can reuse it, isn't it? Something like that?
Yes. Yeah, that part we will do next time. That means after you train the model, you can save those weights and we can reuse. And also while the model is training, because some trainings take hours and days and weeks. So you sort of just save so-called checkpoints. So those things we have to consider. Okay.
So if you want to test this model now on actual data, will you do that later, sir? Like, can you put in an image, or how will you test that it's
Yeah,
actually working?
actually you are testing. With test, so training accuracy, because your computer test accuracy. No?
Okay, so it's automatically testing on that. Okay.
I put that code also. I click the tab button and got that code. So you can see you are loading from test loader. So then if you have your own images, that means own handwritten images, you have to resize them to that size and you have to learn how to get them loaded using PyTorch data loaders. These tutorial data loaders. So please find that out how to do that. I myself do not know that.
Okay.
So maybe you can type that in ChatGPT and ask how to create a loader. I have a network. I have a CNV trained for MNIST with PyTorch. I want to test it with my own handwritten images. Give me the procedure. The data thing is slightly cumbersome, so it will give you the procedure. So it's important, and the size is to 28 by 28, typically normalized, within or normalized. Then you can see transform. So it's opening each image. So it is giving one image at the time, but I want to use it using a load. Yeah, my question was on using a data loader. So see, like that you have to put them. So this is the directory structure. In the zero directory, you have to put image one, image two, one, and so on. And then data set and data loader. So yeah.
Okay, so I think there's a data pipeline.
Annoying details are there.
It is like a ETL or something, like you have a data pipeline and then sort of convert it in a certain format. I think.
Meaning ETL means?
Extraction, load, transform, ETL
Okay.
in data
Right.
process.
Yes. Yeah. That's okay. So I think these questions are very helpful because we can understand practically how to do how you do this. So one important thing is in this case you have to resize the images to the exactly the same size as this model is using. So here they are keeping this one compressed in compressed form. You can see, you cannot see the images. They are compressed. You can see the train images and so on are there. Okay, so let's go back to the slides. I hope you understood some of these things. Okay, so what we studied was the Lenet 5, and we studied it and we coded that. And I think with this knowledge, you can architect a small convolutional neural network and by hand code it using PyTorch, and using a data set, you can get it trained. But unfortunately, I did not talk about the creating your own data set part. I myself have not done that, so please do some studies on that. Yeah. Okay. So one of the existing data sets is this so-called ImageNet data set that has 40 million data points and 20,000 classes. But what is most known is the ImageNet large-scale visual recognition challenge, which has about 1.2 million images and 1,000 classes. And these are 224 by 224 images. So this is the competition that drove this deep learning up to this stage. Actually, on this data set, the top 5 error, that means out of the top 5 retrieved classes, what is the correct one there? That's called top 5 error. And they were making about 30% errors, 25% error by 2011. In 2012, as we described, the AlexNet came and the error was reduced by such a large number. These kind of things do not happen in computer vision. So the whole scientific community was seriously surprised by this result. So that's how deep learning became famous. So now we will talk about that AlexNet. I don't know whether I showed pictures of the 3 people who are behind AlexNet. Here is a picture of those people. This is Alex Krichevsky. This is Ilya Sutskever. This is Professor Jeffrey Hinton. So you can see that he won the Nobel Prize. And Ilya Sutskever actually was the chief person behind OpenAI. Ilya Sutskever. Alex, I don't know. Okay, so you can see it's a great contribution. I will briefly describe that and do a detailed analysis of this network. So they say that they use 227 by 277 images. It is to be seen. So although, but in their network, this is the original actual diagram that was there on the paper. So you can see they ran 11 by 11 kernels. I will show a better picture later. And they had 2 GPUs, the top GPU and the bottom GPU. This is the top one, this is the bottom one. These are graphics processing units, actually 3 GB GTX 55080 NVIDIA cards. So they ran 48 convolution kernels in the bottom GPU and 48 convolution kernels in the top GPU. So those were 11 by 11 convolutions in the first convolution layer. So because they used the slide 4, the resulting tensor was a 55 by 55 tensor. And of course, the depth of that tensor was 48 plus 48, sort of 96. So then they ran again, they ran max pooling. So due to max pooling, of course, you know that the tensor size reduces in, and then they had oh, 128 that we will see later. So this is max pooling again. So that's a convolution, okay? Convolution and max pooling, both these things are there. So again, a convolution here, and then that resulted in 128 channels, 192 channels, 192 channels again, 128 channels, and so on. Then you can see the fully connected layers. So similar network to LNet, but max pooling and ReLU nonlinearity. So the very famous ReLU nonlinearity rectified linear units were introduced by these people. More data and bigger model, 7 hidden layers, 5 convolution layers, and 3 fully connected layers, 65,000 units and 60 million parameters, 2 GPU cards, 50 times speed up over CPU, trained on 2 GPUs for a week. And then they had the so-called dropout regularization also. This is this original NeurIPS paper linked to that. Okay, so a detailed analysis on this network now. So we will discuss this in about 15 minutes and finish. So you can see the 227 by 227 image here. And 11 by 11 convolutions run on them. And the slide is 4. So these are our formula. Remember, 227 minus the kernel size 11, no padding, divided by the side plus 1. So you get 55. So you get 55 by 55. And how many kernels did you run? 96 of them. Okay, that's the tensor depth or the number of channels. And then they had overlapping max pooling. So 3 by 2 max pooling with type 2. So 55 minus 3 divided by 2, you get 27. Yeah, 27, and the 96 remains there. So you can see it's slightly different from the previous diagram that we had, but this is much easier to understand. And then you have convolution, 5 by 5, padding is 2, So you can see that you can get this from the previous formulas that we learned. And then 27 is the resulting tensor size, and because there are 256 kernels, the depth is 256. Then again max pooling, so you can see the size becomes sort of half, and again convolution, so size remains because of the padding, and that many convolutions, 384 convolution kernels. Then again convolution, and the size remains because of the padding, and 384. Then again convolution, 256 convolutions, and you can see the numbers here. And then no max pooling, and then size becomes 6 by 6, 256. That is equal to 9216. Fully connected to 4096, fully connected to 4096, and fully connected to 1000, and softmax is that. Softmax means just raising each number to the e to the power and dividing by all these e to the power, so that you get a sort of probabilistic interpretation of those 1000 numbers that you get. Okay, so we will do a detailed analysis now. Okay, so this is the XNet. So first, let's take the first convolution layer. And input number of channels is 3 because these are color images. Height and width are 227. Output number of channels is 96. Kernel size is 11. Stride is 4. Padding is 0. So what is the output number of channels? Of course, you have it here. I have written 96. Output number of channels is 96. So height, output size, height, and the width. How do you compute that? Input size minus k times 2 times padding divided by the stride, right? So this is how you compute. So this formula, please remember, and then you get 55 there. So output size is 55. And then let's compute how much memory is required to hold this output tensor. So to compute that, we have to consider the size of that. Size of that is number of elements divided by bytes per element and divided by 1024 to convert it to kilobytes. So output number of elements is C out times H prime times W prime, right? And then each element has to be held by 4 bytes because we need to use 32-bit numbers to hold it, no? 32-bit floating point number. So divide by 1024 to make it kilo, then 1134 kilobytes. How many parameters? You can just have to consider the number of kernels and the kernel size and the input number of channels to consider the number of parameters. So let's do that calculation also. Okay. So parameters, weights plus times plus biases. C out times C in times K plus C out. This is the regular computation that we do. 34, 35 kilo parameters, 35,000 parameters. How many floating point operations? To compute that, we have to consider the output structure size. That means 55 times 55 times 96. That's the size of the output tensor. To compute each element of this tensor, we have to run a convolution, right? We have to compute that cost. Okay, here is how we do that. Number of floating point operations multiply and number of output elements, operations per element. So number of output elements is because we have 96 convolution, 96 channels in that, and the height and width are 55. 96 times 55 times 55 times 3 times 11 by 11. Because our convolution kernel spatial size is 11, and then the image has 3 channels. So you can see 105 million floating point operations are there. 105 million floating point operations. Is there any question about this? This is an important calculation. Okay, let's move forward. So I will not do for all the other ones. So only let's consider pooling one. So the pooling is size that it receives is 55, obviously, and input number of channels is 96 from the output number of channels here. So these get reflected there. You can see kernel size is 3 and the stride is 2. So we can compute the output number of channels, size, W prime, and so on. So 27 is what you get, and then memory, and then number of no parameters and no computations. Yeah, it's almost zero, right? Then I will not compute the other one. So please compute them on your own and see. We will do one fully connected layer. So after the flattening, you have 9,216 elements in that, and that is connected to 4,096, right? As you saw before, the flattening size is this much. It's connected to 4,096. So how many parameters must be there? So FC6 parameters, C in times C out plus C out. So we get 32 million parameters. And then what is the size floating point operations for a fully connected layer? C in times C out. That's the now, because all the nodes are connected to all, because there is multiplication here. 38 million operations of floating point operations. Yeah, that is our full analysis of the AlexNet.
I have a question. Normally,
Yes.
in these LLMs, we define the size of this model by number of connections, and we mention some number. Is that the similar thing you mentioned here, like it's 37 million?
I did not hear very well. What you're asking is, when you define the size of an LLM, what is that? What does that size mean, right?
Compared to what you're mentioning here, the 37 million, like, because I know nowadays, like when they define the sizes of LLMs, they mention certain billions of interconnections or something. So are you referring to the similar thing here? Is 37 million?
Yes.
So out of those two you mentioned, which is the one we should be referring to, the one on the left or the right side, out of those two numbers? At the bottom of the analysis? At the bottom, sir?
With this or this?
No, right at the bottom, you had a 37 million, something like that. 37 million.
This one?
I think you did some calculations, sir. I think I saw 30, something like a 37 million. Yeah, right at yeah, somewhere there.
Okay.
So,
So
yeah,
for this layer, we did a calculation. So we did the calculation for for now there are that many layers in this. Now there are 8 layers. For all of them, we did the calculation.
yes, this one.
This
You
one,
just
okay.
passed the
Yeah. Okay.
37 million.
Calculations of all now in this one. All these things in this one, that's a total memory requirement that we need. We have to add all of them because there are that many layers now. You have to add all of them to get the total memory requirement.
Okay, sir.
Yeah. So that has to be held in the computer in the GPU memory to be able to do this computation.
Yeah. Okay.
And then we have to do calculations. How many calculations are required? This many calculations are required for each image. So then there are things like you don't totally learn all the things, and then you have a batch of images, not just one image. Then the batch has to be considered. All these things are there when you compute the amount of GPU memory or the graphics card memory that you require. And when you have multiple cards, how it is done, all these things you have to consider.
Okay, thank you.
Yes, yeah. So this is the important question. So, but if you take something like if you take some LLMs like expression models. DeepSeek models are available.
So I think you have put a filter on the left-hand side. Maybe you need to remove that. On the left-hand side, you put text generation. Maybe you should
Text,
remove
yeah,
that.
these are text generation ones. I cannot at once find the set of models here.
The DeepSeek is there, sir. Yeah.
DeepSeek is there. You can see.
Yeah, the number of parameters. Are they, when you did your calculation, are you referring to the same thing? Number of
Yeah,
parameters?
yes, 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 yes.
Parameters.
So there's a little bit of a thing about this so-called mixture of experts that I want to show you now. So mixture of experts means there are 284 billion parameters, but actively computing ones are 13 billion. That kind of a thing is there because of this mixture of experts architecture. So you can maybe copy it to ChatGPT and ask it to explain you that what
Okay,
this means.
okay,
Yeah,
sir.
so two things. So in regard to large language models. Something more complicated than that uh, because of the mix of expert architecture they have. Ask it to explain this to us. So mixture express model is not a single monolithic network. The model contains many subnetworks called experts. A gating network decides which expert to use each token. It is like you have several people serving you. So maybe a security guard sends you to this desk, that desk, and so on, right?
Like the multi-agent architecture.
Exactly, but it's not exactly multi-agent because you can be served by two agents at the same time, three agents at the same time. That kind of thing is there. These experts are slightly smaller than experts that you think. For each input token, they call it tokens. You can consider them words. Each word, only small set of full model is actually used. This is called the sparse activation. This is the key understanding the parameter numbers as that follow. So here, 1.6 trillion parameters, 49 billion activated, DeepSeek V4 Pro. Total parameters is 166 trillion. This is the sum of all experts shared layers. It reflects the capacity of the model. Activated parameters 49 billion, only 49 billion parameters are used per token during inference. The rest are inactive for the token. So explain CPU. So although the parameters are activated, memory is required. Yeah. Estimate GPU memory for a model like you need to separate what must reside in memory and what actually used forward backward passes. So you can see many things are there in this, right? So to answer your question, it's slightly more complicated than a simple model like that when you take normal models. So memory means the model weights are there. That's what we computed, right? In our example, model states activations. That means when you compute output, what are the output numbers that are the activation? Then gradient. So you need the gradients, right? Remember? So for all these things will have to be kept in the computer memory and the KV cache. So we may not get time to study about the transformers. There's a thing called KV cache. Those things are also there. So you can see. So this is what we only computed. All other things we did not compute because it's anyways ours was a very simple convolution neural network. Yeah. So I think that is some kind of a good point to stop today tonight. So you can see when you consider the memory, memory is very high in the early layers, low in the uh, outer layers because the image size is large, size is reducing as the stride equals 2 is happening. And then the number of parameters very less in the early convolution layers, very high in the fully connected layers. The computations are very high in the early convolution layers, then very low in the fully connected layers. This is the regular trend of a convolutional neural network. Yes. So if you have any other questions, we can discuss. Otherwise, if you don't have any questions, you can log off. So thank you very much for participating. I'm sorry for not giving a break and continuing like this because that happened because of the coding problems that we had, that I had actually. Thank you very much. Have a pleasant evening, everyone.
Thank you, sir.